When the internet was first built, engineers needed a way to give every computer a unique street address. They decided to split the 32-bit address space into big blocks called classes ABC. The idea was simple: a class would tell you how many houses hosts could live on a street network at that time. Most companies were tiny, so a Class C block, up to 254 houses, seemed enough. But as the internet grew, the fixed-size blocks became a problem. A big university that needed only a few hundred hosts could not use a whole Class B block up to 65,534 hosts, because most of those addresses would sit empty, wasting precious numbers. Likewise, many small offices were forced to share a single Class C block, which left no room to grow. The one-size-fits-all approach caused address exhaustion and made routing tables huge, because routers had to separate entry for every class block. These limitations motivated the move to a more flexible system, classless inter-domain routing CIDR, which allows networks to be any size, not just the predefined classes. In a classful system, the 32 bits of an IPv4 address are divided into two parts, the network part and the host part. Which bits belong to each part depends on the first few bits of the address. Class A, first bits 0, network bits 8, host bits 24, total networks 2 to the power 7 minus 2 equals 126. Hosts per network 2 to the power 24 minus 2 approximately equals 16,777,214. Class B, first bits 10, network bits 16, host bits 16, total networks 2 to the power 14 equals 16,384. Hosts per network 2 to the power 16 minus 2 equals 65,534. Class C, first bits 110, network bits 24, host bits 8. Total networks 2 to the power 21 equals 2,097,152. Hosts per network 2 to the power 8 minus 2 equals 254. Class D multicast, first bits 1110, remaining fields not applicable. Class E experimental, first bits 1111, remaining fields not applicable. The first bit or bits act like a label on a mailbox that tells you which neighborhood class the house belongs to. For example, an address that starts with 0, like 10.0.0.1, is in Class A, so the first 8 bits 10 identify the network and the remaining 24 bits identify the host. The -2 in the host count removes the all zeros network address and all ones broadcast address, which cannot be assigned to devices. CIDR, classless inter-domain routing, removes the rigid class borders. Instead of saying Class C equals 24-bit network, we write the address followed by a slash and a number that tells exactly how many bits are used for the network. This number is called the prefix length. Example, 192.168.10.0/24 means the first 24 bits, 192.168.10, are the network. The remaining 8 bits are for hosts, exactly the same as a Class C block. But we could also write 192.168.10.0/26. Network equals 26 bits, hosts equals 6 bits to get a smaller subnet. A variable length subnet mask, VLSM, is the practice of using different prefix lengths inside the same larger network. Just like cutting a big pizza into slices of different sizes, depending on how many people are at each table. VLSM lets you allocate just enough addresses for each department, saving address space and keeping routing tables tidy. Explanation: to find out how many addresses a CIDR block contains, use the formula. Number of hosts equals 2 to the power of 32 minus prefix -2. The -2 again removes the network and broadcast addresses. Example 1, 10.0.0.0/8. Host bits equal 32 minus 8 equals 24. Hosts equal 2 to the power of 24 minus 2 equals 16,777,214. Example 2, 172.16.0.0/20. Host bits equal 12. Hosts equal 2 to the power of 12 minus 2 equals 4,094. To calculate the range of usable IPs, start with the network address all host bits equals 0 and add the host count -1 for the last usable address. The next address after that is the broadcast address all host bits equal 1. Step by step for 192.16, 8.5.0/26. Prefix equals 26, host bits equals 6, 2 to the power of 6 equals 64 total addresses. Network address equals 192.168.5.0, 000000000 in host part. First usable equals 192.168.5.1. Last usable equals 192.168.5.62, because 63 is all ones. Broadcast equals 192.168.5.63. This arithmetic works the same way no matter which prefix you choose. You only need to count how many bits are left for hosts. Routers keep a table that tells them where to send each packet. In the old Classful world, each network entry was a whole class A, B, or C block, so a router that connected to many customers needed thousands of separate entries. CIDR lets several nearby networks be summarized or aggregated into one larger entry called a supernet. Think of a librarian who groups together several adjacent shelves under a single label, instead of writing a separate line for every book. Example, suppose a provider owns 4/24 networks, 198.51.100.0/24, 198.51.101.0/24, 198.51.102.0/24, 198.51.103.0/24. Because the first 22 bits are common, they can be written as a single /22 block, 198.51.100.0/22. The router now needs only one entry instead of four, reducing memory and speeding up lookups. This technique, called root aggregation, dramatically cuts down the size of the global routing table, which is why the internet can still function with billions of devices. When moving from classful to classless, existing networks are split into smaller CIDR pieces using subnetting. Imagine you have a big garden Class B network, but you only need a few small flower beds departments. You draw fences subnet masks to create the exact sized beds. Identify the original classful block. Example, 172.16.0.0/16 Class B. Determine the size each department needs. Suppose you need HR 200 hosts needs at least 256 addresses /24. IT 500 hosts needs 512 addresses /23. R&D 50 hosts needs 64 addresses /26. Allocate CIDR blocks in order of size, largest first to avoid fragmentation. IT 172.16.0.0/23 covers 172.16.0.0 to 172.16.1.255. HR 172.16.2.0/24. R&D 172.16.3.0/26. Document the mapping so every device knows its new mask. By carefully cutting the original block into variable length pieces, you keep the total address usage close to the real need, and you can later combine adjacent unused pieces into a larger supernet for future growth, or for advertising to other ISPs. Modern enterprises often have many locations, VLANs, and services. Using CIDR, the network design team can allocate address space that matches each requirement without waste. Typical workflow: gather requirements, number of hosts per site, expected growth, and any special zones DMZ guest Wi-Fi. Choose a private address range. Most companies use 10.0.0.0/8, 172.16.0.0/12, or 192.168.0.0/16. 10/8 gives the most flexibility. Create a hierarchical plan. For example, use the first octet to identify a region, the second for a building, the third for a floor, and the fourth for hosts. With CIDR, you can decide the exact prefix for each level. Region A 10.0.0.0/12. Building 1 in Region A 10.0.0.0/14. Floor 2 of Building 1 10.0.0.4/22 provides 1,022 hosts, enough for all devices on that floor. Apply VLSM, smaller subnets for server farms /24, larger ones for employee workstations /23, tiny ones for point-to-point links /30. Document and automate. Use IP address management IPAM tools that store the CIDR notation, generate DHCP scopes, and keep track of utilization. This method ensures that no address space sits idle, simplifies routing because each level can be summarized, and makes future expansion a matter of carving out the next free CIDR block. Real-world analogies. Think of a library that assigns shelves based on genre region, then author building, then series floor. Using flexible shelf sizes, CIDR means the library never runs out of space for a popular series, and it never leaves empty gaps between shelves. Security policies often refer to IP address ranges. In a classful world, rules were written for whole classes, which could be overly broad. For example, in a CL that allowed traffic from Class C network 192.168.1.0 would unintentionally open access for every device in that /24, even if only a few servers should be reachable. With CIDR, you can write precise CL entries. Permit IP 192.168.1.64/26 any. Allows only the 64 addresses from 192.168.1.64 to 192.168.1.127. Deny IP 10.0.0.0/8 any. Blocks the entire private 10/8 space. Useful for protecting a DMZ from internal traffic. Because CIDR lets you aggregate many addresses into a single rule, the CL list stays short, which reduces processing overhead on routers and firewalls. At the same time, the ability to create tiny subnets /30 for point-to-point links, /31 for RFC3021 limits the attack surface. An attacker can only see the few hosts that actually exist in the block. In summary, classless addressing gives security teams the granularity to allow exactly what is needed and the efficiency to write fewer, clearer rules, improving both protection and performance.